Okay, so this is going to be fairly short and sweet. Actually, I'll keep Mike on schedule quite easily, I think. So a gentle warm up for everybody. It's not too taxing, I hope. What I want to talk about is how I've been using formal verification in the design of our interfaces. Some quite low-level interfaces. I don't know how many people are aware, but Broadcom's always been very big on synthesizable verification IP, mainly because we use it a lot with emulation. And one of the advantages of having synthesizable verification IP is it also works with the formal tools. So as a quick overview, I'll tell you a little bit about what synthesizable verification IP looks like. Show you about how to use it as part of the development of your interface specifications, how to structure the assertions, how to deal with some of the non-synthesizable parts of the verification IP, and try and draw a couple of conclusions. So synthesizable verification IP is often structured around the Acceleroscemi standard, which basically shows how to sets a standard for how to map these things onto emulation boxes, and essentially it's achieved by having a synthesizable part of the design of your verification IP, which maps onto your emulation box. The synthesizable subset, it's at least sort of DC synthesis, but a lot of the vendors support a little bit more. And then there are DPI calls, system verilog DPI calls, which are used to communicate between the synthesizable part of the design and the unusually C code running on a workstation next to the emulator. And the reason we've gone this way is because it gives us a smooth transition between simulation and emulation. There's very little overhead in terms of what it does for your simulation times. In fact, it's quite beneficial because your synthesizable parts of the transactors tend to be translating between wire level and transaction level, so that means you've got a good transaction level verification environment. So typically everything inside the yellow box is synthesizable Verilog or system Verilog with DPI calls in it, and everything in the blue box is C++. And the yellow box goes on your hardware, and the blue box goes on your workstation. So one of the things about the transactors is they provide an executable specification of your interface. You very often find that if you develop your verification IP at the same time as your protocol specifications, you'll find all sorts of little corner cases and gaps in your spec, and you get a much stronger specification by doing it this way. You can also use the verification IP as an example of how the protocol operates. You can take it through corner cases, capture waveforms, and show it to people who are trying to actually implement real hardware on the interfaces. We typically construct a test bench for the verification IP, which looks a bit like this diagram, where you've got a master and a slave, and the monitor running tests through those, taking them through the transactions, making sure we get coverage, making sure that your bus functional models can actually drive into coverage corner cases as well. And so, we get through a lot of verification IP errors before we even get close to the IP development. We can also thrash out corner cases of the protocols and so on. And then typically all of your assertions will go into the monitor. And what we can do, as well as running this sort of test bench, is you can set up some proofs where you bind the monitor to either the master or the slave and try proving your monitor assertions about the individual components of your verification IP.
What assumptions do you have here? Is this a sort of mixed simulation and formal environment? Explain about constraints. or am I thinking off the path? Can I talk to you maybe about it later?
Yeah, maybe. I'm not completely sure I understand not sure I completely understand the question. So yeah. So what you find about the assertions that you've written in your monitors is they'll fall into roughly 4 categories. So at the top level, there's stuff which the master has to obey, and there's other stuff that the slave has to obey. And then you find there are properties of the transaction which you're trying to drive into the through a master which needs to be obeyed, and that tends to come from assumptions about what the C code is producing. And on the slave side, you'll find there are some properties of the response generation as well. So there are necessarily some non-synthesizable parts of the transactors, and you need to make some assumptions about those when you're trying to prove these assertions as well. So that means you can structure your assertions. You can tag each of them with which bit of the system is supposed to be guaranteeing that this is true. And that means that, for instance, when I'm trying to prove something about my slave, I can use all of my master assertions as assumptions, and vice versa. And then what you find is that you come to trying to prove that your master satisfies all the assertions that you expect to be true of a master, and you find actually you're missing some assumptions about the slave. So, for instance, we have a bus where you can request 256 bits across the bus, but that can come back in a number of different segments. If you've got narrower buses somewhere in the system, it might get split up and you'll get multiple replies to that request. But there are a couple of things about it. One is that you have to be always replying to an outstanding part of the request. And the other is that you must first reply to the critical word. So when I started trying to prove this about my slave, it immediately became obvious that I'd missed an assertion about the master, which said that if you say this is the critical word, then you must be requesting one of the bytes from it. So simple things like that. You find there are assertions that you're missing, and it just gives you the opportunity to make things more complete. You can also put coverage points into these things and make sure that you're actually hitting those with your verification IP as well. But there are a couple of places where you'll find that there are necessarily some non-synthesizable constructs in your verification IP. So, for instance, the DPI functions that you use for communicating with the C code. And typically you'll find that you'll set up a transaction by assigning a bunch of variables inside a is this a pointer? No. So you'll set up a bunch of variables from an export function, and then sort of drive those into the design. And essentially you need to take this non-synthesizable function out of the synthesizable portion and model the variables that are being set up by that function as inputs to the design. Some tools will actually automatically decide they don't understand about export functions and do that for you. But if they don't, you need to black box those. You need to make those variables direct inputs yourself. So that's one of the typical things that we have in our code, which we need to work around. The other one. The other one is just in some places you do end up putting non-synthesizable stuff into your synthesizable parts of the design because you'll get more control in simulation than you will in emulation. So, for instance, you might be randomizing something in simulation where you'll hardwire it in emulation because you're really not so bothered at that point. So occasionally you'll end up with randomized functions here, which obviously don't work well with formal. So the idea here is, so for instance, on this one, I'm trying to generate a mask, but I want to make sure that my mask has one of some set of bits set within it. And so I make an assertion and an assumption about this. So gem mask here is the thing that's being randomized, and therefore you want to set that as a primary input effectively. But it has some constraints on it because it has to satisfy this constraint here. So there's two things you want to know. First of all is, can that constraint be satisfied at all, which is the precondition of the randomized function essentially. So we want to put this assertion up in front to say that mask has to be non-zero, otherwise we can't satisfy the we can't randomize the variable. And once we have randomized it, we can assume that the constraint has been satisfied. So therefore, we've got an input which has become constrained according to the randomization the randomization constraint. Yeah, so I mean that's going to tell us that when we're doing our randomization, we're not going to go outside the bounds of the other assertions that we've got and so on. But also it's actually quite handy to have proved this precondition here that when you get to this randomized statement, it's not going to fail. Yeah, so that's basically it. So I mean, conclusions. I think you're developing the verification IP alongside your interface definition. We get the executable specifications. We get a better view of the completeness of the assertions. It's a simple proof environment. These things tend to actually go through the proof tools very quickly compared to some of the actual real IP. It's more reliable in simulations. We've proven that we can get coverage. And obviously the synthesisable verification IP means you can accelerate it as well. So that's all I have to say.
Sorry about the drill work, trying to find someone from the hotel to stop it. Any questions? Yeah. So one quick question, Jeff. Are those master and slaves communicating across the bus? I mean, are those bus...
Typically, yeah. Typically.
And I presume those fairly well defined in advance. Is there a lot of reuse from that?
Not well. I mean, what I'm suggesting is that it's not necessarily a system-on-chip bus. It could just be some sort of interface from a bit of IP, and the point is that at the point where you're defining what that protocol is, you're developing the verification IP as well.
Okay.
Simulation. So what kind of molecules do you use to develop?
Yeah, we've been using commercial formal property checkers. Yeah.
Any more questions for Jeff, or should we move on to Julie?
What's the additional value of the property being synthesizable? Sorry.
Well, we typically don't synthesize into emulation. We don't synthesize the assertions into emulation. Typically, we don't have an emulation platform that really supports that yet. So no. But actually, what we've found is that with a lot of these, you can actually prove them about the IP anyway formally. So yeah, it just helps to have ironed out the getting the assumptions right in advance of trying to do that proof on the real IP, because the proof on the real IP goes through better if you've got more confidence that it's actually going to work.
And do you keep those assertions running in simulation even afterwards?
Yeah.
And the reason for that is?
Can't be bothered to comment them out.
At least you're honest.
They don't seem to be expensive anyway, to be honest.
Yeah. Okay, any more? Okay, thank you, Jeff.